So the next one we're going to talk about is support vector machines. Support vector machine, in my opinion, is the most clever idea ever. So this, we also studied a little bit of history about support vector machines. The idea is so brilliant, and people ask, oh, wow, how could somebody think of this? It took a long time to actually arrive from the initial idea to the final algorithm that becomes useful. But support vector machines can be used for classification and numerical prediction. For numerical prediction, the algorithm is called support vector regression. We're not going to cover that in this class. Support vector machine has been shown to be very robust, to have high performance in many domains. It was compared to a neural network handwriting recognition algorithm and support vector machine 1 at that time. So anyway, we will see why it's so powerful. So I divided support vector machine slides into 2 segments. The first part, we're just going to go over the intuition, try not to touch on the math. The second part is all about math, and I'm going to skip this in this lecture. There is a link that you can actually look at the entire mathematical derivation of support vector machines online. The professor featured there is much better fitted to explain the math behind it. So anyway, so support vector machines can separate linear and nonlinear data. We're going to show why is that and what are the things that support vector machines do to achieve this goal. We mentioned it right here. The idea is to map a nonlinear mapping data from the original training data space to a higher dimensional space. And then once the data in the higher dimensional space, you can always find a linear optimal separating hyperplane. When we say always find this hyperplane, this is always a global maximum. This is because the function that we will try to optimize is actually a convex function. So earlier we saw that convex function is basically just a curve with one single minimum or maximum point. So in this case, in those optimization questions, you can always find global maximum or minimum. We're also going to talk about support vector machines being robust, meaning that it's not very sensitive to your input data. The hyperplane going to separate training examples with maximal margins. We're going to talk about what are the key parameters, hyperparameters that you could adjust in using a support vector machine and what their effects going to be. So since any higher dimensional data we cannot really observe visually, so we're going to use this simple example in 2-dimensional. We have 2 class data from 2 classes that we need to separate. So there, in a 2-dimensional space, we need a line to separate these 2. In a hyperdimensional space, we call it a hyperplane, but it's always linear. So in this case, how do we separate this? So this line could separate these 2 classes perfectly, but this one can too. This line can too, and this and that. All those lines can separate too. But which one is the best? Intuitively, I think we all agree B1 is the better line because the data are separated further apart. There are broader margins between these 2 groups of data. This contrasts to B2. This dot and this dot is almost on the boundary. A little bit of switch in this line, we could actually start to misclassify things. Or if we observe some other interesting examples from either of the class, they could locate it here or here, and they're going to get misclassified. So we want a decision boundary that separates these 2 classes the best. The best referring to that they have larger margin on either side of this hyperplane. So there's some definitions. I have this. Right. So since we decided this is we would like to find this hyperplane as our decision boundary. We want to maximize this margin. So when we look at this, this decision problem can be formulated as this function. If for the dots, so this line has a formula of this, and this line going to be like this, and this line is that. Okay. Oops. So we know well, mathematically we can find the margin, then will becomes the magnitude of the width, the weight factor 2 divided by the magnitude of the weight factor. So the weight factor is right here. Then our boundary here is basically saying that for all the points that's greater than 0, so they reside on this side, this is going to be our class 1. For all the points that goes below this line, this is going to be our negative class 2. So support vector machine was designed for binary classification problem. There's 2 classes we want to separate. So then what we just described can be formulated in mathematical terms that we want to minimize this term. So earlier we say we want to maximize this, and after we did inverse, it becomes minimize this term. And our condition is we want all those class 1 on one side and class 2 points on the other side. So this is our constraint that express that idea. We started with this minimization problem, but this problem turns out to be exactly the same as this maximization problem using nonlinear programming optimization methods. So here another variable alpha is introduced. This is Lagrangian multiplier. So we can find alphas that maximize this equation that gave us exactly the same solution as the solution that we would like for this minimization problem. What is important to observe is in this optimization problem, this is input training examples. One example and another example, and this is a dot product of these two. So this suggested that we actually, the optimization solution is dependent on the dot product of those input observations. So this is one point we need to remember. It turns out when we need to classify new examples, it's also dependent on a dot product between 2 observations. So solution, when we optimize this function, what kind of alphas we're going to find? It turns out we're going to find most alphas being 0. A few, a smaller number of alphas going to be non-zero, and those alphas actually represent the support vector. Aha. So we neglected to explain support vectors in this slide. So support vectors are the vectors that on the boundary, I mean on this the edges of those widest margin. Support vectors is important in support vector machines because they basically defined Knowing those, you basically defined the decision boundary, and also support, because it's only the decision boundary is only dependent on the support vectors. If you remove all other data points, just keep the support vectors, your algorithm is going to give you exactly the same result. So this could also be seen as error noise reduction method. Maybe also can be used when you don't have. We'll mention that later when you have imbalanced class problems. Even though this class may be smaller, but if you actually have all the support vector machines in your data set, having smaller number of observations actually does not affect the final result if you actually have those support vectors included in your training example. I think one part of the beauty is they figured out that alpha is directly related to the support vectors. Any data point that is not a support vector, that they're going to have an alpha that's 0. Support vectors are the only alphas that has non-zero values. And because the equivalence of the optimization problems, it turns out that the weight that we were looking for is just a weighted sum of all the support vectors. So this is our support vector, those observations that are support vector. Those are the alpha values that we optimized and learned. This Y is the label of those support vectors, whether it's a negative one or positive one. So this is going to give us the weight. But we don't actually need to compute explicitly this weight because remember our decision function? So here, this is our decision function, right? This is our decision boundary. So if we plug W into this decision boundary with a new data Z that we're trying to classify, we're going to see that the value of this decision function is dependent on this inner product, dot product of these two between support vectors and the new data. So one new data versus all the support vectors. If this formula turns out to have a sum that's negative, then we will classify Z as class 1 and otherwise class 2. So through this process, what we just described now, we can use the support vector that we just described now to separate two classes if they are linearly separable. If we could find a good line that actually give you a boundary, a margin that's wide enough to separate two classes. But a lot of times we don't have linearly separable data. I want to stop right here and ask if you have questions so far.
Yes, I have a question.
Yes, go ahead.
This +1 and -1, is this always 1 or is it arbitrarily chosen?
Oh, it normalized to 1.
Okay, thanks.
As you can see, you can just normalize that to 1 by apply a different appropriate denominator. Yes, all those ones, and so okay. Using 1 and adding those squares and take the half of that is all what is known as mathematical convenience. It makes the following computation easier and result easier to interpret. That's it, but yes, this is 1. Other questions? Okay.